Hello, everyone, both here and on Zoom. So I have the pleasure to introduce Dr. Michael Zink as our guest speaker today. Mike is the Barrows Professor for Geophysical Sensing at the EC department at UMass Amherst, and he is also the co-director for the Barrows Center for Atmospheric Research. Mike has a very wide-ranging research expertise from geophysical sensing to cyber infrastructure to multimedia systems, test beds, you know what. So, and he's also the PI for the Open Cloud Testbed and a co-PI for the Massachusetts Open Cloud. So he has his ends on the resources up in Massachusetts. So if we need them, we can ask Mike. And he's a longtime collaborator of myself on different projects. And he's also an active member of the FABRIC project as well. They have a FABRIC rack up there. So without further ado, I'll let Mike talk about Cloud Square.
Thank you so much, Anirban. It's a pleasure to be back here. Thank you for, in such a nice way, say, jack of all trades, master of none. That's kind of, what I sometimes characterize myself. Becoming more generalist, I think, is the term throughout my career. But combining my, systems research in the computer engineering area with science, and science here in this case is atmospheric science, but science in general. And I think that there's every day I discover new nice connections between the two, because computing has just become so important for all the sciences. I have friends in social sciences, they use models and whatnot to make predictions, and what other kind of talk to people on using LLMs to make predictions on elections, and apparently that's very accurate. But that's for a different day. So it's wonderful to be here. We're just everyone's trying to get our memory back. I gave a talk here more than 10 years ago. I think it's about time to come back, so it's nice to be back. And thank you all for coming, and especially I see this when I saw this earlier. There's a good amount of people online. Please, I'm kind of old school. I hope I include everyone. So if you have questions or whatever, if someone can make me aware when you pick them up. I want to talk for about maybe 40-45 minutes to then leave enough time for discussion. This is a little bit of an experiment. I'm trying to bridge the gap between the kind of two larger research areas I'm in, and I hope that works out, but it's not too confusing for everyone. So if you have any questions, I like interactive talks, so if you have any questions in between, please feel free to interrupt me and ask for clarification. So Cloud Square, and I'll come up and try to explain why I came up with this time. Taking this one to a glance. Okay, so I want to talk about my systems research first a little bit, the connection to FABRIC with the Open Cloud Testbed, and what we're doing on this side. We're doing a lot of work in what's called feed programmable gate arrays. That is a type of accelerator that's not too familiar. Everyone knows GPUs these days, I'm pretty sure, but we're using different type of accelerator and see how that can be used for, at the moment, more advanced networking research, but hopefully for other research applications in the future. And we just demoed that last night. I will briefly talk about how we integrate with FABRIC on the site, which is very exciting. And then I want to introduce Barrows Center for Atmospheric Research. Some of you know that we had an NSF Engineering Research Center at UMass that was called Collaborative Adaptive Sensing of the Atmosphere. About 3 years ago, Jerry Parros came in. He's a UMass alum and made a really nice donation, an endowment. And so we have a new center with a slightly different focus. We had last 20 minutes. I'm going to talk a little bit about this, and then I want to kind of try to see how these two pieces integrate in terms of having research compute and advanced computing and advanced networking supporting core sciences. In the example of mine. Just this is not an introduction of the talk. This is a little bit more of an introduction of myself. I did a wonderful job on it. One couple extra words. So I've been involved in building research infrastructure also, because as a systems researcher, you need infrastructure to do your research, right? Everyone has different approaches. The mathematicians can all do it with pencil and paper, and systems researchers need infrastructure. So, this is, I think, where we first met was within the Genie scope. I've been a co-PI on Cloud Lab on its onset. I'm the PI for the Open Cloud Testbed. So that's all kind of research infrastructure. That's the computer engineering research. And then I've been co-director for CASA and now co-director for Paris Center for Atmospheric Research. So this is more of the really application side in terms of research and science. And I've been also doing from way back from my PhD side, a bunch of work in multimedia systems and multimedia distribution. And I do this for fun. I always put, so my last name is Zink, right? So this is the structure of the zinc atom. So, this is kind of what I'm made of. The joke is actually, so I'm from Germany. The fun fact is that my mom's maiden name was the German equivalent of steel. So I'm a really metallic person. Okay, coming back to what I'm talking about, right? So Open Cloud Testbed. So what we, so this is now it's called computer research. No, so it was CCRI and they changed, and NSF changed the program. So this is really building research infrastructure for the site for people who do research within the size of Berlin NSF. That's kind of maybe best characterized it. And the idea on our side was that, yes, there were, Cloud Lab and Chameleon were already out that supported cloud systems research, right? Most people go out and say, why don't we need that? Because we can go to Amazon and Azure and Google Cloud. But if you want to do systems research, you really have to get under the hood and you have to be able to change things on the cloud operating system, for lack of better words for that. And you cannot do that in commercial clouds where they run this operation, right? So you need equipment where you can do this. And we wanted to do this in a way that we can, first of all, dynamically scale it based on resource requests. And then also, as something that cloud providers already, commercial cloud providers already have also in there, but do not open this up to the research community is using FPGAs and expose them to the research community. If you know something about it, anyone used an FPGA before here?
Long time.
Okay, right. So you have to program them, right? It's not like a CPU or GPU. You really have to put code on that FPGA, and so that is something that is a little bit more complicated, and we build a workflow for all this, and so users can do that. So you can come in, get a bare metal server with an FPGA, put your own code on it, and run whatever you want. We do this within a very large ecosystem. Massachusetts Green High Performance Compute Center. We have a really large compute center that is a consortium between major institutions in Massachusetts. Yale just joined, so it's going beyond Massachusetts, and so we have an ecosystem that involves. I don't want to go through all the acronyms, but you can see there's a lot of collaborations going on between research institutions in New England. And I'll mention some of them when it's ready. What we built is actually a test bed, which, the concept you have to think of this mostly this test bed. I don't want to go into all these details. I just hopefully give you a little bit of an idea of the size of this test bed is that when you come in as an experimenter, you get access to bare metal servers, right? So you have your own server and you can install pretty much whatever possible without breaking any substantial rules on that server, right? If you invented a new operating system that runs on the hardware, or supported by the hardware, you can install it, right? And so you can run, if you came up with something better than Docker or whatever, you can install it there and then test it out at scale, because we have over 200 servers in that test bed. So it's not just something you can do in your lab, but you can also do it in the side. And we think it's important to just not do this in isolation. And so I apologize, but if you look over here, we tie directly into FABRIC. We have a FABRIC rack in that same data center, but we now open it up on the networking side so that you can run experiments that go across the world pretty much with the international version of FABRIC. Down here in the corner, you see we have we have general compute, but we also have about, I think by now we have a total of 40 FPGAs available that can be used by the research community or anyone who's interested in experimenting on that side, and we make them available. The other important component of that is, I think I get to speak about this in the next slide, is what they have network interfaces, and we make them also available to the research community. Right? There's a couple concerns about that because these FPGAs have two 100 gigabit interfaces. So if you do something stupid, you can really do some damage on the network. The great thing is that this is like same as in FABRIC or in other test beds. The actual data plane is isolated, right? There's no connection to the public internet. It's not that you all of a sudden can stream out with 200 gig into the public internet and cause havoc there, right? So that's the isolated part, and that's good because some people like that for security research, because sometimes you want to run certain things you should never run in the public internet, right? Because that's going to cause all kinds of problems. And so it's nice to have these test beds to try these things out. So you see a little bit more of the detailed infrastructure here on the left-hand side. We have these almost 40 FPGAs. This is not, there's some new stuff coming in as we speak. Almost 40 FPGAs available. See a little bit how we put them, how we network them together. Each of them most of them have two 100 gig interfaces. Down here, you see actually a new version that is AMD's idea of playing into the AI world by building, by coming out with a specific model that's designed for inferencing. So you can actually deploy a machine learning model on that FPGA and then run inferencing on an FPGA. The idea is that FPGAs are more power efficient than GPUs. Speaking of that, we also have a site, I don't have this mentioned, but don't have this on the slide, but I want to mention this here. We've worked with my colleague David Irvin, and we have instrumented it in a way that we can also do very accurate power measurements. So we have PDUs that make power measurements, so we can also, when we run experiments, accurately see how much power is consumed by the servers, depending on the jobs. That's obviously something where a lot of people who work in sustainable computing are very interested in. So we can expose that to the researchers. They can do this for the analysis. I don't want to kill you with all the details of the different FPGAs and all this. I'd be happy to answer any questions maybe afterwards if there are any. Again, what I said very early on, if you have used an FPGA before, this is not, you kind of have this, but we have this internalized on a regular general compute system. You take your GCC or whatever, you compile your code, and you have an executable you can run, right? With an FPGA, you program actually the circuit, so to speak, on the board, right? And that's a little bit more complicated to do. And to make this a little bit easier, what we did, besides making the hardware available, we built a tool flow. What that means is we have in the high performance compute center, we also have a cluster that's basically a cloud, and we deploy VM there with all the tools installed that you need to develop. In FPGA jargons, what you do is you develop a bitstream. That's what you can. That's the application you can run on an FPGA, so to speak, right? And so we have all this. We have this whole tool flow installed. If you're ever interested in doing something with the FPGAs and OCT, you can get an account from us. You can go in there and can use all the tools you need to develop your bitstream. And I think AMD was also kind enough to allow us to use a little bit more lax licensing model. So once you're on that system, you can just use the licenses we have there instead of having to bring in your own license to use these tools. And then you can actually deploy them. And what happened 3-4 years ago is since I've been in contact with FABRIC team members. And Ilya at the time came and said, hey, you're doing all this FPGA work. I think you're putting them also into FABRIC. And so then, we had a close collaboration. And so you can actually, run the bitstreams you develop with our workflow also on FABRIC FPGAs and can run experiments there. We see it also in a way of a 3-tiered approach. You can develop bitstreams on our cloud VM. You can test things in OCT because it's easier. I wouldn't have to go too much into detail, but it's more streamlined to test them out and run them. And then you can go into FABRIC and actually deploy them and run larger scale. Right? Ours is really a cluster with many FPGAs in one location. FABRIC has the same number of FPGAs, or around the same ballpark number of FPGAs, but in many locations. So if someone is interested in a wide area test, you want to use FABRIC because that's much better suited. Small side effect for those who kind of are in those details. We use bare metal servers on the Open Cloud Testbed. So every time, because what you have to do is to get your code activated, your bitstream activated, you have to reboot, right? You have to power cycle the FPGA. On FABRIC, it's a little bit of a problem because the FPGA sits in a server that's used by many people, right? There's a bunch of VMs running. And so if you reboot the server, a bunch of people are going to be upset because their VM is going to be rebooted. So Mert, who's fantastic, he's doing fantastic support for us. We have been working on that. And that's why you want to really test your bitstream on OCT, because you can reboot as many times as you want without impacting anyone. Once you figure out what you have developed and what you're running is as stable as possible, you can bring it over, talk to Mert, get it deployed, and then hopefully run an experiment. But you don't want to disrupt this on the FABRIC. It's just, there's nothing good and nothing bad about it. It's just two different models how you do this. And I think we've been learning a lot by trying to deploy this across test beds. I think that's super exciting, but also super hard is when you try to, bridge between different environments that for good reasons have been developed under different aspects, under different loads, but then you want to bring this together. And actually, I just talked to Keiki, PI for Chameleon on Monday, where we're doing similar things now with the FPGAs, or doing similar things for the FPGAs. So this is what we showed last night. Some of you saw that already. The FABRIC team came up with this wonderful functionality of a facility port, enable the facility port in the Massachusetts Green High Performance Compute Center in Massachusetts, where our equipment sits. And now we can actually connect over layer 2 between FPGAs in the Open Cloud Testbed with FPGAs in FABRIC. And now we can actually do large scale experiments. Here we do this just in a small setup, but we had a bunch of interesting demo nights. Are always great because we had a bunch of interesting discussions last night about how we can scale this up, do more wider scale experiments. Talked about a little bit with Kamal about functionality and whatever we need. So I think this is just great to be here also because there's some side discussions we have on very interesting topics. So again, this is a demo we showed last night where we in the end, pull up slide on that. No, where we add a little bit of extra header information into Ethernet packets, which you then can use for, it's called in-network telemetry, timing information you can stick in there. You can also put a little routing information in there and use it. And the nice thing is with the FPGAs, you can stick it in at the ingress and take it out at the egress. And then if your packet has to travel on, it looks just like a regular Ethernet packet, like nothing happened ever before. But in the core, where you have this capability, you can do all kinds of, imagination is all kinds of interesting things what you can think of doing with that, mostly for kind of telemetry and measurement applications on the network side. So there's a little bit of a focus on the networking side, but you want to just give a couple of small examples. And I think an interesting side effect of that, this is of one of the students. So this is a collaboration with me and Lisa at Northeastern, and her student just implement P4 as a networking programming language where you can program switches. Since FPGAs are programmable and have a network interface, you can also use it to program. You turn your FPGA into a Smart NIC and can give it specific functionality and offload some of the networking functionality that's performed in your operating system onto the NIC. So with really high bandwidth, that comes in very handy because all of a sudden your server doesn't get bogged down by all this, switches and interrupts and current and context switches you have to do on the kernel. You can actually do this on your network interface card. Kind of offloading, which is already now implemented in many firmwares of regular NICs, is maybe the core example. But you can do much more, right? And so here, this is just a small example where we do layer 2 forwarding. So we look at the MAC address and can then decide what port to go out. And that's certainly no rocket science, but the interesting side effect of that is we did some measurements, and the really interesting thing is on the FPGA, because you keep all that operation local at the FPGA, and FPGAs are really, there's no multitasking, there's no time sharing, right? It's almost like a real-time operating system comparable to this. You can see if you go up to reasonable packet sizes, you can do this at line rate, right? 100 gig interface, we get 100 gig throughput with that operation. And that's something which you would not get if you use a standard NIC in a server that does whatever, how many processes. Right? So that's kind of interesting. And that is actually one of the reasons if you look at, Azure did this a while ago. So commercial clouds now some of them have FPGAs in the clouds, because you can imagine in Amazon Azure, all the applications that run in the cloud, often very distributed, there's a lot of networking going on. And there's a lot of networking going on that's virtualized, right? So you have a ton of VMs that all have virtual interfaces, but it actually boils down to a physical interface at some point in time. And that becomes your bottleneck. If you can do that with an FPGA, if you can do decryption and encryption for some of the secure applications on the FPGA, you can actually take a lot of load away from that poor server, when we characterize it this way, and run it, right? And so I think that's what we see. The problem, again, as I mentioned at the beginning, the commercial cloud use it for their own operations. There's no way for a researcher to get inside or run even everything. So we can do this here. And here's an example of getting throughput. We took part in the Network Graph Challenge. That's something that they run at the HPEC conference. And the student led that. It says my internet connection is unstable. I hope everyone can hear me just fine. If anyone cannot hear me fine remotely, please let me know, or not see the slides. Hopefully it's just a temporary thing. So here the idea is to do flow characterization. So when a packet comes in, you have the 5 tuple IP addresses, ports, and protocol, right? And you want to use that to say this packet is part of flow 1, this packet is part of flow 2, this packet is part of flow X. Done all the time for firewalls, intrusion detection systems, and so on. All good? Mm-hmm. Okay. And again, so what we did is we implemented this in an FPGA. The problem here is it's not just a single lookup, because you also have to have a table that has information about all the flows, right? And you have to then update that table based on, maybe you want to count how many packets belonging to a certain flow go through your network interface. And so the student here, Han, developed a bitstream that was kind of novel in a way that it uses the P4 language on one side, but there's on the FPGA, it allows externs, so you can add functions that are not defined by P4 and uses high bandwidth memory to then use the table management. And if you look at the table here, again, if you go to a reasonable packet size, I should have corrected this. Sorry, I forgot. Gigabits per second, right? Mm-hmm. So you can actually go up to almost 100, again, almost up to line rate with even for flow identification, right? And then, so I think that's again another interesting result. If you look at, people develop very specialized systems to do such kind of applications, and then I think it's to be able to do this at line. Why can we not keep up for smaller packets? You all know when your packets are much smaller, you have to send way more to keep the volume, data volume up, right? So that's an issue. But for a reasonable size packet, you can do this pretty much at line rate. And as we know, because of this issue in data centers and in other places, there's a trend of going into jumbo packets that are even almost 10 times bigger than the normal Ethernet packet to find. But takeaway message from here is, and I apologize, the colors, fade a little bit here on the projector than compared on my slides. But I hope you can see still relatively okay. The takeaway message is that you can do can get real performance improvements if you all do this on the FPGA, because again, everything you do is just happening between the network and the FPGA. You need this is still incoming traffic from the network.
you need your host just to install the bitstream, the program on that, and power it. So to speak, right? Everything else is independent. Has some really interesting implications also for people who look into disaggregated computing. I don't know if that's something people look at frequently, but now you can actually allocate resources in different, independent of the server it's hosted. I just want to mention that very briefly. We have a whole suite of applications we have developed that people can use to learn how to build on things like, calculator. This is for in-network processing. So you get data in from different sources and you want to do a merge or something like this, then you can actually do calculations on the two data streams and then send one combined data stream out. We have done this in a way up there where it's reconfigurable, so you can actually, when we say calculator, it's a little bit an overstatement. You can exchange different mathematical functions for calculations on the fly, so you don't have to, reprogram your FPGA. So there's some additional examples. Sorry, I forgot. There's also, we have a link to that with we have several tutorials, and we have a Git repository with all this the workflow and the examples I've shown here, the code for these examples on them. So if you guys are interested, let me know. I can certainly point you to that. Deep breath here because I'm going to change topics a little bit. So I want to see if you guys have any questions on.
Keep an eye on chat, so we'll see if we can. Oh, there we go.
Oh, sounds good. That's good news. Okay, so this is on the cloud and advanced networking side, and so switching topics a little bit. I'm also involved in activities that are related to atmospheric research. You see our wonderful donor couple here, Jerry and Linda, who supported our center, and the center. The Paris Center for Atmospheric Research builds on actually what we've done over 20 years in the NSF Engineering Research Center for Collaborative Adaptive Sensing of the Atmosphere. And the goal with the new center is, right, you want, if you do something, if you have a new center, you want to do something new. You just want to build on what you've done in the past, but also include new topics, new research, and new people. And so here, CASA has been mostly on weather observation, but we're looking out also to work more with the climate community on our campus a bit better. And so that's what we are. It's a process, it takes time, but we're trying to build this up. The mission is really, look at climate and weather because it has an impact on our daily lives. Today it has a very, very positive impact. It's warm and sunny. We enjoy that. Right, but you all know, right? We talked about hurricanes just a moment ago, right? Hurricanes, flooding. I mean, flooding. If you look globally, I think flooding, whatever the source for the flooding is I think is globally the biggest problem, the biggest threat. And with changing climate, it's not gonna get any better anytime soon. These are actually images. Left side is Sandy in New York, and right hand side. And right-hand side is actually, I think it's Lowell in Vermont, summer of 2023. No one had ever imagined that, but tremendous flooding events in New England, right? So we see this is happening all over the world. It's just a snapshot of how weather and climate impacts society. And so our goal is actually, the long-term goal is to contribute with science outcomes on mitigation for the impacts we have from weather and climate change. And I think that involves not only the remote sensing scientists, the atmospheric researchers. It goes all the way out to social scientists. One of my colleagues, my co-director in PCAR, she works a lot with emergency managers and the public in terms of, how do they react to warnings? What's the right thing, right? So there's the flooding thing is what doesn't know what don't drown, turn around, right? Because most of the death in flood events are actually people driving through underpass, right?
And so it's not only it's often not only the science, but it's also getting the right message out. And so this is our overarching goal. Let's go a little bit more into the research here. Obviously, on the atmospheric side, winds are really important. On that side, how do we detect and predict winds? Precipitation estimation, so we can predict forecasts. And then very interesting phenomena I learned about over the past 20 years about my career is infrasound. So sound that's below 20 hertz is a phenomenon that's created by many atmospheric and geophysical events. And how can you sense that and also use that for any kind of scientific application? Distributed sensing is important because the more we sense, the more information we have, but then there's a challenge. Now we have all this information, how do we use it, get the right products? And that's where, I think I see this very important link where we need the networking and the computing side to get this information, to make all this information to something in a useful product that helps us, not only on the research side, but also on the warning side, right? So that's important. And then I'm not working on this in this area, but my colleague Brenda does, and it's the mission of the center is obviously hazard mitigation. But because now, if you learn something about weather, climate threats, what can you do to make the impact as small as possible? So that goes out to, and that's really exciting because you work all the way to social scientists with social scientists. So here's one of the examples. We did this a long time ago with our original test bed in Oklahoma. Tornadoes give off an infrasound signature, right? And so you can actually, this is one of the devices our Jonah manufactures. These are very, very sensitive barometers. To give you an idea, if you take that device and you put it in a room, you lift it just up by that, you see the pressure change. So very, very sensitive. It's used all over the world for different applications. Brian, here you see the porous hoses I was talking about. So wind is your enemy, right? Because wind, right, where you're sensing is adding a lot of noise, and you want to filter that out so you can see the infrasound. You can detect the infrasound noise from a tornado. And here you see an example. This is frequency and over time, and the color scale shows you the coherence from the signal. And you see here the signature, infrasound signature. This is, between this goes all the way up from 0 to 2 hertz. So very, very low frequency, right? That's given off by a tornado that was 200 miles away from where we are. So you can observe events. Low frequencies travel really far. So we can observe the events. We actually did some triangulation because we had 3 different locations, and we could even determine the direction that's coming from. And you see again how this nicely correlates when you have the signal, when you have the signal from the tornado. We did something that is weather unrelated, but still atmospheric measurement. And the idea came about, I don't know, we had a discussion and then we figured out, I just flew in here a couple of days ago. You fly, right? And you probably realize that sometimes when you approach, it gets a little shaky in the airplane. That's often because there's a big plane right in front of you and it's creating a big vortex, right? And the FAA has some very fixed rules on what the distance is. So if like A380, right, the biggest Airbus plane, they make the double decker, right? If that's in front of you, and you're in a regional jet, you have to keep so many miles from that plane, right? But that's just a, that's a rule of thumb, right? With wind and atmospheric conditions, things dissipate in different ways, right? And so what we set out to is measure the wake vortices of landing and starting aircraft with these infrasound sensors. And we got lucky. We have an Air Force Reserve base in our neighborhood, and they allowed us to deploy sensor very close to the runway. We thought they would never agree to it, right? Because It was funny because we had radios and the student was out deploying it and they said, hey, he's really got to come off there because the C5 is going to take off pretty soon. And so what you see here, again, it's unfortunately fading a little bit. So we deployed these sensors close to the main runway. And we did this with they have, biggest military transport airplanes the Air Force has, because we were lucky to do it with them because they create some really good turbulence, right? And then as you can see here on the dotted line, here, this is when an airplane landed, and you can see here, again, relatively faint, but still clearly detectable D-wave vortex that's caused by that airplane landing. And you see, and with that, you can actually then see how long it takes to dissipate when you would give clearance for another airplane. So that's the goal. There's a ton of additional research that has to be done. This is very complicated for us because we can only go out there when they allow us to go out there. We don't have a permanent deployment. We have not managed to convince any large airport that has, real civil, like, if you would go to RDU, it would be hard to run around the runway and do this stuff. Because we were interested in seeing, what are the signatures from other types of airplanes? How is this when you have much higher frequency? But it's interesting to see, at least for us, it was an interesting data point to see that this is possible in general. Sometimes you get really lucky. So we had a student undergrad who joined the project because he helped us build the sensors we deployed out in the airfield. And then he said, I'm from Taiwan and I'm going home over break. What about I take one of the sensors? Because we knew you can, earthquakes give off infrasound. What about I take a sensor home? And by the way, my dad is a professor in the civil engineering department. And it's not Tsinghua, it's a different university in Taiwan. We have some locations where I think we can deploy it. So, well, let's do that. Cool. And so, he stuck 2 of these sensors in a suitcase. Obviously, I had to work with compliance at UMass to make sure he's all doing the right things and all that stuff, and deployed them in 2 locations on the island. And on April 3rd last year, they had a really big earthquake. And I always feel this is when you work with disaster, you always feel kind of bad because you have something bad to happen, get some good data, hurricanes, tornadoes, earthquakes, right? But we were able to measure the earthquakes and the aftershock. So here you see with 2 barometers, you see the main earthquake and an aftershock of that. This is just the pressure amplitude, and here you see the power to the spectral density of this event. Now, what's really interesting, again, infrasound, very low frequency. We have a barometer placed at UMass in Massachusetts, right? Here you see the earthquake and the signature from the earthquake and the aftershocks also, right? So that signal, an earthquake signal, if the earthquake is strong enough, this is always one signal, but others have shown that a signal from an earthquake can travel around the globe up to 3 times. And it's so low frequency that it bounces back over the atmosphere. So you can see that, right? That helps with observations in terms of impact. This is not, I want to be really clear, this is unfortunately not something we can use for warning, right? Because we can only observe. We see on this one, and there's no proof for it, we see a little bit more of a ripple effect before the event, but we're not sure if that is really a signal that an earthquake is coming. I think that again takes lots of data, and unfortunately for that, we need many earthquakes, which we really don't want. But you can observe this, and you can observe this from very far away. The question is, if you really had a network that spans the globe, can you then really learn something, right? We're now throwing machine learning at many of these things. Can you actually run models that would then help with doing predictions? Because maybe if you measure small tremors all over the place, you can say something, predict. So very interesting. I never planned of doing this. This was really a student running into my office and say, hey, why don't I take some of the sensors to Taiwan? We still have them out there still running. And hopefully we can get some more good data out of this. And what we also do, because this comes out of CASA, we still run a test bed of 6 radars down in the Dallas-Fort Worth area. This is for severe weather observation. So weather radars to measure, precipitation, and then to make measurements about severe weather in terms of severe thunderstorms, supercells, tornadoes. So that's one of the other aspects. We do. So let me, and we're doing for a long time. Actually, the nice thing is this is now, and I'm going to speak to this in a moment. We now have more than 10 years of data from the testbed. And that's, from all I know from the climate community, now we're at the turning point where this turns from weather data into climate data. Because if you have observations from 10 years on, it becomes more of a scale. It's really, if you think of the age of this planet, it's nothing, but it becomes a little bit more of a longitudinal data set that goes into the climate area. So, and what we do with that now, that's interesting because now we have a 10-year data set, right? And we can actually go into like everyone else, into the AI area and say, what can we do with this data set, right? How can we train models and what can we, is there a way to get improvements? Now, the first thing is, again, Brian, we talked about this earlier, right? So you have data. Now there's researcher X and says, give me all the tornadoes that happened in the last year, data from all the tornadoes happened in the last 10 years, right? How long does it take you to get that data? To sort this out forever, right? So I have a student who is working on this. NSF. NOAA has the storm events database. We have our own database. So we're putting this in a database. People can search it, and then get data sets based on certain events, right? It doesn't have to be tornadoes, it can be rainfall and all this, to make it really easier for the research community to just obtain the data. So you don't have to, kind of get your graduate student for a year just to compile the data set to then run any kind of analysis experiment. What we did is Open Storage Network. I don't know if you heard about that. That's another NSF project. I don't know if you have a node here, but there's nodes all over the place. We have one in the data center. So we took all the 10 years of data we have from the Casa testbed and put it in an S3 bucket. And now it's available over, a standard, what I would call a standard interface today. And so people can do searches. They get actually compilation. They get an email with links, so they don't have to download the data locally, and they can actually run the compute where the data is, and do whatever kind of, experiments, algorithms they want to run on the database on the cluster. So that's step number one. And then what we did is actually nowcasting, so very short-term weather forecasts, right up to an hour, because that's important for severe weather events in the terms of severe storms, convective events, right? Thunderstorms, tornadoes, because they happen very shortly. So you want to be able to generate forecasts quickly, and nowcast is one approach to that. And so we took our data set, and again, we ran into this issue of, now here's a data set, but how do you make it, sorry for using an unscientific term, massage your data set so it's actually usable by a machine learning model. And so you can see here, we took almost 10 years of data from June 2016 to 2024. This was a combined set between rainfall data from the big NWS NextRed radar and our testbed. And we had to do some adjustment in terms of cropping, data range. Interesting enough, that brought down the data size down by an order of magnitude, and temporal resolution. And then also looking into, since we want to make predictions about rainfall rates, right? Data that does not have this clear air, we could all kind of pretty much throw that out. So, we had 96% of the data had no rainfall information, right? Because if you look at the testbed is in North Central Texas, when it rains really hard, but it doesn't rain often there, right? So how do you deal with all the data? So I think what's important also is when you do these kind of things, where you have a domain science and you want to use AI and machine learning for it, you really have to understand a lot about the data. Otherwise, it kind of can backfire terribly. And so what we are doing right now is actually, we're using, there's a new AI model coming out pretty much every day, right? But what all these people do is they rarely compare their models with each other, right? All the models also have not, sorry, I skipped that, I apologize. Our testbed uses X-band frequency, which there's only a few weather radars in Europe that use it. Everything else is S or C band. So we're looking how these models work for a certain frequency band weather radar, right? And looking at models that have been developed in the past and comparing them with. And that's, again, where the computing comes in. We have created a workflow where you see on top, the top row shows you the original data as observed by the radar or the radars. And then we run this with a bunch of models and compare the quality of the models. Right? So this is, it's not directly, there's nothing stochastic there, right? So it's not really an ensemble, but it's a comparison between these models. You could almost use it as an ensemble because you can see, you know, how do the models agree or disagree with their nowcasts, right? And so we're looking into that, and we also, this gives us information on how we have to adapt these models to a different type of radar in this case. So that's what we are in the middle of right now. And this is where, you know, I kind of conclude that brings the two clouds together, right? This is weather in terms of clouds and cloud computing. And I think the interesting aspect where FABRIC comes back in now is when you look at this on a large scale, we're doing this with our testbed in Dallas for the West. But if you would do this nationwide, or maybe globally, right? Now you have the distribution aspect. What can you do in the edge? Right? What can you do? What do you have to do centrally? So what I'm trying to characterize here is, you know, sensors all over the place, edge computing, and you know, FABRIC folks don't get mad at me if I characterize FABRIC as edge computing, but it has some aspects of this because it's very distributed and can often be, right, there's a FABRIC node at tech, right, which is close to where our radars are. There's a FABRIC node right where we have our compute sitting in Massachusetts. You know, you can imagine kind of how this plays out, right? And then you have the core with very high network connections, and you know, I didn't get this into the central cloud here, but also again compute, right? So you can do in-network computation, and then you have the core cloud, the big clusters, right? The ones that are more academic, like Chameleon, what we do in Open Cloud Testbed, and the commercial ones like AWS and Google Cloud and so on. And the interesting part to that is actually that now you can bring this all together because you have data from some sensors on the edges. And then you have, like, for example, the Sustainable Data Initiative at Amazon. They store all kinds of weather and climate data and make it again publicly available through an S3 interface. Not only radar data, but also satellite data. I think maybe, I don't know, I think data from some models and so on. So you can actually now really run algorithms that get information, machine learning algorithms that get information from all kind of sources. And so I think this is where, you know, and what's important is the core science part comes in about what sources really make sense. Where does a new source contribute something? That's not always clear. The systems part and the computer engineering part comes in of where do we store the data? Where do we do the compute? Where do we have efficient distributed systems that make this all work? Because I think the more we do these kind of things, the more sensors we get. You know, every day you get so many new sensors across the globe. The more data we have, you cannot do this in one central location. It has to be distributed to be efficient. And this is what I'm trying to just to characterize a little bit on my last slide, is that when you look at machine learning models, right? And you look at certain forecasts you want to do, like really for events like tornadoes that develop on a short scale, you want to keep as much as the edge at the edge as possible. Otherwise, you know, it's just taking too much time. And so, can you do local training? Can you do local inference, right? So from sensing to getting out the warning to the user, can you shorten that path and you don't have to go all the way back to the core cloud, right? And does this work together where you have a local model that you update periodically, and you have a global model that you maybe constantly train, right? Because you get new information all the time. Sorry, I didn't put this in here, but your global model would not only be informed by your sensors. This could be, as I just showed on the slide before, all kind of climate data that you get, right? Could be satellite information, could be something like rain gauges. It might be important for rainfall rates. So how do you do this in an efficient and distributed way? I think is a very interesting question. We know that, the most efficient thing is if you can, you just put it into one location, right? That gives, but we see and we know that that's not always possible. And if you can't do that, what can we do? And I think for me, the really interesting challenge and curiosity question is, yes, we can as computer engineers on one hand, we can go together and we can say, we can do this, and we can do that. But is that really what the domain scientists need, right? Does it make sense to have such a distributed AI model? Or is it just throwing something in that makes it less precise, less accurate, less efficient, and so on. So I think that's really questions we have to ask ourselves as an interdisciplinary team, because otherwise we will not find the right solution. Okay, so let me summarize. I talked a little bit in about the systems and the domain science research I do that spans advanced networking, advanced computing, and cloud computing, and also atmospheric sensing. I do also some work in the area of sustainability, and that goes together. On one hand, we talked about the challenges we have through weather and climate, and making using outcomes of our research and the side of sustainability here to protect, individuals and the environment, society, but then also computing. So David Irwin is a colleague of mine at UMass, and I and our students look into, this all takes a ton of resources. So how do we make that sustainable? We're just talking about this. I heard something the other day that large language models are driving up electricity prices, right? Because all these data centers now need power like crazy, and the power is going to the data center, not your house anymore. If you want it at your house, there's demand, right? Demand increases the price. So in some regions, electricity price is going up for even private households. And so how do we do that? And we don't want to talk about all the side effects of generating this electricity, right? So that's important. So how can we make all this a little bit more sustainable? Again, I've been lucky enough to collaborate with some of you for many years now, and I'm always interested in new collaborations. So this is where you can find me. So if there's anything you want to discuss, I'm here for the rest of the day. If there's anything you would like to discuss or have any questions, be happy to talk to you. Okay, but I'm happy to take any questions.
Questions from Mike?
Yeah. I'm stuck on the infrasound problem. Yeah. So the idea that the infrasound emitted by a tornado 100 kilometers away, does that imply that it's pretty low frequency but high power? And why does the local wind turbulence contaminate that part of the spectrum? Because that should be relatively high frequency.
But it has a low frequency component, right? So we also see the low frequency when you look at let me go back to this one, right? So yeah. Here you see the spectrum. And then again, sorry, it's fading out a little bit here on the projector. But you see there's a good component on the very low frequency, right? And that is actually been generated by an airplane, right? But you still have low frequency component of that turbulence. Yeah. And then it's infrasound. So we have done, I haven't put this on here. What we did is we went out to Vermont where they have a Met Tower, where they have anemometers at different altitudes.
Right.
And we put a barometer on the ground to see what infrasound signatures we get from wind at different altitudes. So the wind component, and that's a problem for us. There's a strong, the high frequency component is not the problem for us, but right. there is a low frequency component in wind turbulence also that is in the infrasound that we're seeing. And that's, so you see here, that was a very calm day, right? But you see here where the low frequency component of the wind on close to the at the boundary is actually causing quite a bit of noise.
Turbulence kind of looks like white noise, so it kind of covers the whole spectrum.
Kind of. It's too bad. I have some power density plots that shows you you always have well, first of all, you always have a DC component because here, if I go back to the earthquake part, the trend on the line here, you see that trend is just barometric pressure, right? So there's a high and then there's a low moving in, right? So you can always that you can take out really easily, right? So yeah, but you have sorry, what was your question again? Sorry,
I wasn't a question, but there's perhaps an observation that said maybe turbulence looks more like white noise, so it's across the whole spectrum. So you also
Right,
have a low
right,
frequency.
Right, you always have a strong component in the lower frequencies, and then it is relatively evenly distributed until I don't know exactly. I couldn't mean so it dies down at a certain higher frequency, but I don't exactly off the top of my head know what that frequency is. Right? But that's what we've been seeing with the barometers. Right? Again, this is only one way to measure it. Right? People use anemometers and other things.
Can I ask a question?
I was
Somebody
Eric.
else is okay. Yeah, I'll let somebody else go.
Eric, do you want to go?
Yeah, sure. Wake turbulence is kind of dear to my heart. A friend of mine landed his plane upside down that way. Looking at how it works. So like on a foggy day, with the vortex, you can actually see the vortex spin maybe a couple of times a second. So there should be a very strong 2 hertz component mixed in with a huge amount of noise, or at least a fairly strong component. That's what I imagine. Is that sort of what you're saying?
Yeah. Again, I don't know how well you see that, but so where I'm pointing right now, this is like the 2 hertz threshold, right?
I see. Yeah.
And you see it's not, we would have liked to see that a lot stronger, right? But this is what the outcome of the measurement is. But you see a stronger component. You see it all the way up to the 10 hertz, but it's it's less stronger than in that 2 to 0 hertz component.
I was worried down at the bottom of the graph that might be 1 over F noise, but you feel like that's real?
Yeah, because it's not there, it's you see some of it a little bit more when you have more wind coming up. So this is more wind noise, right? But this is really at the moment the plane was touching down, or shortly after the plane touched down, because we didn't have the sensor right at the point where it touched down. It was a little bit further down the runway.
Exactly. I should learn to read graphs in 3 dimensions. Have you ever had a chance? I haven't dealt with a wind profiler in literally 10 years. The acoustic ones, I don't think have a chance at a wake vortex, but the laser ones were just becoming a thing, and I never got to play with one.
Yeah.
Do you know of anybody that's done that or tried to cross correlate it with acoustics?
There has been work with using LiDARs to characterize wind vortex also. Yes.
Okay, thanks.
Ashok?
I think Sarah had a question too. He's got his hand up.
Okay.
Yeah, thank you. This is Sarah Varunachalam. Fascinating talk. You covered a lot of breadth, a lot of ground on different topics. But interestingly, my question is on the same slide. I heard a lot of discussion on this, and it's interestingly mine on the same one. So I like to study air pollution through physics and chemical processes. And one thing we're doing right now is for the FAA, trying to develop a new local scale dispersion model to model dispersion from aircraft during landing and takeoff cycles. And there are 2 specific processes we are looking at amongst many others. One of them is the plume rise from a hot exhaust plume that comes from the aircraft jet exhaust. Given the very, very high temperatures, you have a rapid elevation of the plume, which some of the current regulatory models do not account for, and we're trying to capture that and evaluate against observations. The other thing is this wake vortex issue that you described here, and it looks like the picture you have is probably a C-130, a cargo plane, I think, I'm not too sure. But what I'm wondering about is with this technique that you have, can you capture vortices from commercial aircraft at a commercial airport like say Boston Logan and others, given the amount of aircraft activity happens say within an hour or so? is that something that we can do based upon what you're describing here?
So honest answer is I don't know. And again, so this is so what we did, we were out there for 2 days. This is a C5. We also had C-130s and what's the one that has the propellers? So we had 3 different military aircrafts there. We could see the vortices from all, wake vortices from all of them. We had a private jet come in that day, and we didn't pick up anything. Also, that was at a time where the wind was picking up, so we don't know if probably a less powerful vortex with more wind noise if it got drowned in the wind. So we're not sure. What I would love to discuss with you is actually, since you're working with the FAA, if the biggest problem for us is really someone to allow us to do a long-term deployment at an airport, at a big airport like Logan or even at DFW, we had not had any live yet. I want to mention one data point for you that might be, it's not air pollution. What DFW reached out to us about was actually in another aspect of pollution, and that is they wanted to know exactly where rainfall happened over the airfield when they are running de-icing operations, because the rainfall washes the chemicals of the airplane and the ground, and it goes into the sewage, and they wanted to know of that pollution happening. And slightly different than the problem that you have, but I don't know if it's the FAA, but at least the airport operators are interested in that type of.
Yeah, thanks for that comment. I would like to follow up with you. I have 2 potential angles to follow up on. One, I have collaborators in your neck of the woods in Boston University and Tufts who are doing some field campaigns at Boston Logan. And EPA, FAA are also ramping up another study at Cleveland Airport pretty soon. And I would like to follow up with you and see if some of this can be possibly deployed at one of these 2 other airports. We are looking at other parameters for dispersion.
Happy to talk more. Absolutely.
Thank you.
And two questions. Oh, how much does the infrared sensor cost, or the infrasound sensor?
$5,000.
$5,000?
Right.
Oh, okay.
They're not cheap.
Yeah. And the other question I have, and I don't know if you implied this, and maybe I was reading too much into what you were talking about. So is it the case that you're using your infrastructure that you talked about right at the beginning? Are you using the FPGAs there to design the edge AI algorithms that you then deploy in your?
You can. That's good. That's something that's kind of work that's kind of developing right now. So what would so since there's so much interest in AI, right? Especially so AMD bought Xilinx. So Xilinx was a big FPGA manufacturer, and then they're not part of it. AMD is really interested in finding AI applications for, they have a hammer and a little bit for the right, so to speak. But it's not. I don't think it's totally unreasonable, right? Because they now have a tool flow, and we have used that, where you can actually train a model. You save that model in a standard format. And then you can run a tool flow to generate a bit stream that uses that model for inference, right? And now me and my collaborator and her students have done this. For example, again, you can then deploy that, and then you get information, data you want to run the inferencing on, and just send that to the FPGA, right? So even with a GPU, you still need your host system. And and yes, NVLink and all the stuff, they're trying to optimize this all the time, but you have to go through your host, have to deal with all the memory aspects of that. With the FPGA approach, right at the edge, you can, depending on the size of your model, obviously, get the data. You could maybe get data right from a sensor or whatever, right into the FPGA, run your inferencing there. What you send out maybe over your bus into your host system is the outcome of the inferencing. Or you send it back into the network to somewhere else. Yeah. And so you could think. So what we're doing right now is my colleague Georgia Stewart got a CC Star compute grant. She's a part of our cluster is going to be a new cluster that has GPUs, but on ARM-based systems, because most people who are interested in AI, they don't use the CPU anymore, right? So why put a system with a beefy CPU in there when you run the GPU all the time? What I'm trying to tell her is, let's also stick FPGAs in there, right? So we have a really powerless ARM system there that kind of runs operating system, and the rest is just accelerators where you can run either training or acceleration. And I think we will see kind of more of that kind of trend in the future. And sorry for making a long answer to your question here, but there's two interesting aspects. Yes, you can do it, and I think we have to rethink how we do it even more efficiently than it's done.
So just to follow up, if anybody else has a question, I don't want to hog your conversation. So I get the last one. Sorry, unless you want to ask something.
That's okay.
No.
So the other question I have is the example that you showed us, is the edge computing mostly inference? The local model is just inferencing. You're not really training to learn characteristics of the local environment there, or are you? Like, are you fine tuning to the local environment there or not?
Yeah, I think there is a federated learning story
Yeah.
here as well,
Yeah.
right? So that's on the modeling side that could be done in this.
Right. So we have actually, under different settings, we have looked at federated learning, right? And so you can, I think there is a chance for a generic approach, right? I want to be careful. Generic is too strong of a term. For a multi-use approach, maybe, where you can, do inferencing only where it's appropriate, or where you have the most efficient way is to train a central model, right? But then you send the model updates out to regular GPUs or FPGAs to do the inferencing on. There might be a way. So this is one of the things I'm not, you always want to do things but don't have the time to do all this stuff. But on our track is, so there's almost 200 National Weather Service radars all over the country. Can you actually do federated learning? So you have a model for example, for nowcasting, right? So you have a model, you now deploy that model at the edges, you train the model at the edge, and then you have a federated learning approach that updates your central model, and you push back and update this on that side.
I mean, you can do that, but it seems to me that if you are looking at a spatially distributed application like this one, where the weather in Arizona is very different from the weather in Boston, right? And so why would you want to federate? You just want local learning to happen, to learn the local characteristics, right? And so you just want a local model that can just learn the local environment there and not necessarily get all that back to the big model.
I think that's a very interesting question, because with other trends, they're global trends, right? So we see like temperatures are rising, right? So
that's true. Yeah.
Right. So does it still make sense? Weather is local. I agree with you 100%. But are there trends, long-term trends, where it really where it would be beneficial to have a global model? You don't have to update this on a 1 second scale, right? Where you periodically bring it back together and then send an update out. You run your local inference all the time. You even update that model regularly. But I don't. This is hypothetically, maybe every month or every half year, you send it back. You have you update your global model.
Sure.
Because there's certain things that happen on a much larger time scale.
Yeah.
That we talked about. Hurricane frequency, hurricane intensity. Brian, correct me if I'm wrong, but has certainly something to do with the temperature of the ocean, and that's increasing from what we know right now, right? So there's some aspects that might be, but for some, really, if it's sometimes it's important to have something less accurate but quick, right? And then that makes really sense. Absolutely.
Thank you.
And also, those things are correlated. If it happens in Memphis, it's going to happen in Knoxville 8 hours later. So.
Yep.
Well, thank you all, Anirban.
Yeah. Let's thank Mike one more time.
Pleasure. So great to see you all here in the room and also to see so many people joining on. It's fantastic.